Hi, I'm Phil, and today I'm going to talk about the microbit and a dust sensor that measures particulate matter, PM2.5, and can give us some warnings if the dust level is too high. Okay, last year we started the year with bushfires that continued on from December 2019. And those bushfires not only affected the local area in New South Wales, but they also went global. And here on the top left-hand photo, you can see the dust streaming across to New Zealand from New South Wales. So all this dust in the air, particularly at high levels, is bad for your health. And the most obvious problem is problems with breathing and damage to your lungs. So if you're living close to a bushfire, you not only have the dangers of the fire itself, but there's also the adverse health effects from the smoke itself. And it's not just the lungs. You can have quite sore eyes and do damage to your eyes too. So I'm going to create a project that looks at measuring small dust particles that come from bushfires. And the sort of sizes we're talking about, if you take the human hair, it's around about 50 to 70 microns. That's 50 millionths of a meter. And much smaller than that, at 2.5 microns, that's the dust particles diameter that causes the most damage to our lungs. So that's the one that we focus on. And in this project, I want to measure not only the particulate matter 2.5 microns, but also PM1 and PM10. And to do this, I'm going to use the Seeeduino Grove dust laser PM2.5 sensor. I'm going to use a microbit and also an Arduino compatible computer called the Seeeduino Lotus V1.1. And the Lotus computer will be connected to microbit via a Grove connector. The other Grove connector connects the Lotus to the Grove dust sensor. But we get plenty of help from the government regarding warning us about high dust levels and poor air quality. So on the right, you can see a number of measurement sites throughout Sydney. The closest one to us is around about 8 kilometres away at Prospect. And from that site, the readings of not only PM2.5 and 10, but also ozone and other gases, together with temperature, pressure, and humidity, are reported here over a 24-hour period. And on this particular day, the measurement for PM2.5 was 19. So that was a good reading. So note the color code here. We've got green. Anything below 25 gets a green color code. So we get fairly good support from the government. So if we can get a warning of high levels of dust, we can mitigate against that, do something about it before we're exposed to very high levels. So in this project, I'm going to use the Grove dust sensor. We'll explore that, and I'm using a mind map to do that. And I'll spend most of my efforts on the project. So a little bit about the Grove dust sensor. It's the blue box in the middle, and it's used primarily for air quality testing and real-time and continuous PM2.5 measurement. So you can see its connections on the socket on the left on the blue box. You can see the Grove connection and what each of the pins of that Grove connection, what they do. So the specifications of that Grove sensor are listed here, and we're going to measure 1, 2.5 and 10 microns. The other specifications are the resolution, and an important one is the stability time. That is, you can't really get a valid reading from this unit below 30 seconds after powering on. And the connection for the Grove dust sensor is an I2C interface. And here I've also listed the address of that interface. Well, how does it work? Well, air is drawn into the sealed detection chamber in the dust sensor and is extracted on the bottom. Across the chamber, there's a light beam, and there's an infrared laser that transmits a light beam, which is picked up by a light detector on the other side. If there's any dust particles, they cause scattering of the light, and the light sensor can detect that scattered radiation. After it's detected, the voltage is then amplified, and it's then split into multiple channels. Then there's a small microprocessor on the Grove dust sensor, which prepares it to transmit it over the I2C interface. So here's my project. I'm going to look at what the objective is, look at the hardware of all of these components that you can see in the photo. We'll look at the communications protocols, the software, what the results are, and some references. So one of the hardware items is that I want to display the results on a liquid crystal display, similar to this one on the top left-hand, or the top right-hand corner. So it has two lines. The top line is for the standard measurements, and the bottom line is for the atmospheric. That is the measurements that I collect from the air. And there are three measurements. There's one for 1 micron, the middle one is for 2.5, and the one on the right is for 10 microns. So I not only want to show this on a liquid crystal display, I also want to provide a warning if the 2.5 micron measurement is greater than a good reading. So the color coding from the EPA in Victoria recommends that you use green for good. So if the 2.5 measurement is less than 25, you can use a color code of green. And the other colors are shown here against their PM2.5 upper limits. So how do I implement those colors? Well, I'm going to use a neopixel array, which is capable of producing colors programmed by microbit. So here's the hardware. I'm going to use microbit and with another computer called the Seeeduino Lotus version 1.1, and it's Arduino UNO compatible. It's got lots of Grove interfaces, and these are connected to microbit. Well, one's connected to microbit. And for microbit, there's another interface, and that's provided by an interface board called BitMaker. And BitMaker has 6 Grove ports on it. One of them will be connected to the Lotus computer. The other important device is the Grove laser PM2.5 sensor. And as you can see, this is the most expensive item at US $33. So starting off with the Grove dust laser sensor on the left bottom, we connect that to the Lotus computer via the I2C link. And if you look at the top of the Lotus board, you can see all the Grove connections. So we connect that to the I2C socket on the Lotus computer. Then we can add the microbit computer, and it's sitting on top of BitMaker. And the connection between Lotus and the microbit is via a UART link. So it connects to the UART socket on Lotus, and the Grove cable goes into ports 8 and 14 on the BitMaker. Also on BitMaker, on the I2C port, there's a connection to a 2-line liquid crystal display. And this is where we get some of our results. The other results are using the LEDs in the middle of BitMaker, where it says P13. That label is surrounded by 4 pixels, and we can program any color on the rainbow with that neopixel array. So we just add a bit of software and we're ready to go. But before we do that, we might just explain how the Lotus communicates to the microbit computer. And we call this the UART protocol. So it's actually a series of little sentences or statements which are transmitted as ASCII codes across that line. And for the standard particular matter, they all start with S. So S, M, A, B, and C correspond to each of the PM readings. And we do the same with the atmospheric. So each of these start off with an A. AEA, colon, X, hash, carriage return. That corresponds to readings for PM1, where the value of that reading is X. Now onto the software. So using Microsoft Makecode, this is the code for the microbit. And it starts off on the left, initializing the parameters and setting up the devices that are connected to BitMaker. Then we move across to the right, and in the middle, we've got the processing for the UART. And as the messages come in, they're screened and filtered to update the variables on microbit. On the right, we have the liquid crystal display processing. So a little bit more in detail, on startup, we show the label and we redirect the UART to port 8 and 14 on BitMaker, and we initialize the liquid crystal display with an address of 39, and we add the labels that help us identify the values for each of the standard and the atmospheric values for particular matter. We also set up the neopixel array, and that will be on pin 13 using 4 LEDs. We also set up the thresholds for good, fair, poor, and very poor readings for the particular matter. Then we move on to the forever loop, which just goes around and around. And if a message comes in, it then calls up the display LCD function. And if an event is triggered on the serial line, it's processed by this routine on Makecode. So all it does is slices up the little sentences that come in on the UART, and it then allocates values to the variables within Makebit. The last display, the one on the right, displays these variable readings for particular matter. And there are 6 of them. The first 3 go on the top line, and the other 3 go on the bottom line. Now, the most critical one there that I want to process is called AEC for atmospheric PM2.5, and it's displayed in the middle of the bottom line. So besides the code in Makecode, there's also Arduino software, and I'm using the language called C++ to get that to work. And I'm using a demo program as a template, modifying that for my program. So I won't go through all of the software, but a couple of key points. One is that the headers in the UART messages are shown on the bottom, and these headers are in a string array. So there are 2 critical functions in the code, and these process the values. So the first thing is that they send off the header and then select the value of the PM measurement. And there's an index. So if you look at the bottom function, I is the pointer to the particular PM measurement. And we set up the header first, followed by the value, and it's then transmitted. And before we do it, we also transmit a hash and a carriage return. So you might note that I'm actually transmitting that over 2 UART lines, the standard one, and also an additional soft UART, which is on pin 2 and 3 of the Lotus computer board. And here are the results. So one of those UARTs goes off to COM5 serial port on my PC, and it's picking up all these events. So you can see that the header followed by a colon and the value of the PM reading followed by hash is all I need to get into the microbit. So this was quite a worthwhile project. It all worked, and I've got plenty of ideas for extensions. And one of those will be to use a radio link between the internet and the Lotus computer. And that will that radio link is called LoRaWAN, and it will allow me to place the dust sensor anywhere in Sydney and then connect it to a LoRaWAN radio network. Now, this could be quite useful as I can then put the sensor in vulnerable locations anywhere in Sydney, and then we can get warning. Another project would be to add the GPS measurements to that, so I not only get the PM2.5 reading, but I also know where it comes from. Okay, so thank you very much. That's the end of this presentation.